Hello everyone, thank you for taking the quiz for week 2. So in this video, let me show you the solutions to each of the problems. Okay, let's start from problem 1. So f of 1 plus x over 1 minus x equals x squared, and we want to solve f of 2. So here, let me first solve the expression of the function in the following way. So let me call this method 1. Solve f of x. Okay, once we have f of x, we can solve f of 2. Right, so let's do this way. So we define x, 1 plus x over 1 minus x to be some new variable, say t. And then we try to solve x in terms of t. This gives 1 plus x equals t times 1 minus x, which is t minus tx. And now we group x together. We have 1 plus t, x equals t minus 1. Okay, so x equals t minus 1 over t plus 1. Okay, now let's rewrite this expression. F of 1 plus x, 1 minus x equals x squared. This can be written as f of t, because this is a t, equals x squared. Now x can be expressed by t. So this is t minus 1, t plus 1. This is x squared. So that's the formula for f. We can simply write back to f, to x. This is t minus 1, t plus 1 squared. Okay, and now we want to, okay, sorry, I should change this x minus 1, x plus 1. Okay, so to get f of 2, we just plug in 2 minus 1, 2 plus 1 squared. So it's 1 over 9. So the solution is 1 over 9. Okay, this is method 1. I can also tell you method 2, which is kind of similar. Because we're going to solve f of 2. So let's try to solve x such that 1 plus x over 1 minus x equals 2. Right? And then we can solve 1 plus x equals 2 minus 2x. This gives 3x equals 1. And so x equals 1 over 3. So f of 2 is basically f of 1 plus 1/3 over 1 minus 1/3. That equals x squared by the given formula. So x is 1 over 3 squared. This is 1 over 9. We still get 1 over 9. That's the solution to this problem. Okay. All right, let's come to question 2. Find the smallest positive integer such that the following inequality holds. All right, here we have a equation as follows. Recall that n plus 1 square root minus n square root times n plus 1 square root plus n square root. Okay, this corresponds to the difference of two squares, right? This is the square of the first term minus square of the second term. And we see this is n plus 1 minus n, which is 1. Right, from here, we can express 1 over square root n plus 1 plus square root n in terms of square root n plus 1 minus square root n. In this way, we can express each term in the expression in this way, and we can have a lot of cancellations. Okay, we see that 1 plus root 2 plus 1 plus 1 over root 3 plus root 2 plus 1 over root n plus 1 plus root n. We apply the equation to each of these terms. So this is 1 plus, this is root 2 minus 1. This is root 3 minus root 2 plus root n plus 1 minus root n. So from here, you see that we can cancel many terms. Say this 1 cancels this -1, and this root 2 cancels this root 2, and keep doing this. Finally, we can cancel this root n with some root n in the previous term. So finally, this equals root n plus 1. Yeah. And we see this larger equal to 10. This is equivalent to, we take a square, we take square on both sides. We have 1n plus 1 larger than 10 squared, which is 100. So n larger than 99. Because we want to find the smallest positive integer satisfying this relation. So the smallest positive integer n must be 100. N equals 100. So the answer is 100. Okay, question 3. So here we have this number capital N defined as follows. We want to find the largest integer k such that 10 to k's power is a divisor. Well, by the structure of this number, there's easy way to calculate the value of n. So let's do this. So n equals, we have 2029. So this is very close to 10 to the 2020th power. Okay, and times itself, right? Times itself. And plus 199, 2029. So this is close to 2 times 10 to the 2020. So this is 2 times 10 to the 2020 minus 1, right? So basically we can take 10 to 2020 as a notation. So this is, we can consider this to be x. This is x. So this becomes 2x. So this is like x minus 1 squared plus 2x minus 1. And we can expand this square is x squared minus 2x plus 1 and plus 2x and minus 1. So we have some cancellation. This 2x negative cancels this 2x positive. And this 1 cancels this -1. So finally, we just get x squared. And so this is like a 10 to the 2020 squared, which is 10 to the 4040. So it's clear that the largest k is just 4040. So the answer is D. Largest k equals 4040. Okay, that's the solution. Okay, let's do problem 4. Probability. So we put 3 identical coins to the on the following 4x4 grid. What's the probability that no 2 coins are on the same row or the same column? Right, let's first find the total number of ways to put these 3 coins. Total number of ways. So we apply the multiplication principle. We consider this process as 3 steps. Each step we put 1 coin. So for the first coin, there are 16 squares. We can choose any square to put the first coin. So basically we have 16 choices, right? And then we put the second coin. Because each square can have at most one coin. So there are 15 choices remain. So there are 15 choices for the second coin. Similarly, there are 14 choices for the third coin. Okay, that's the total number of ways to put these three coins in this order. Okay, next, let's try to find the number of valid ways to put these three coins. So same, for the first coin, we can put on any square. So there are 16 choices. But now we consider the requirement. No two coins are on the same row or same column. So if a coin is put on certain square, the second coin cannot put on the same row or same column. So we should cross this row and this column. For example, okay, let me take example. If I put the first coin here, one here, basically I should remove this row and this column. So for the next coin, there are basically 9 squares, 9 choices. So it's basically 3 by 3 square remain. So for the next second coin, we have 9 choices. And then suppose I put the second coin here. Same, we should remove this row and this column. So let me remove this row and this column. And then we have only 4 empty square remained. So for the third coin, there are 4 choices. So this is the total number of valid ways to put these 3 coins. And then let's calculate the probability. The probability is the number of valid ways divided by the total number of ways. Let's cancel this 16. Let's cancel this 16 and simplify the expression. So 15 we divide by 3, we get 5. 9 divided by 3, we get 3, right? And divide by 2, we get 7 here. Divide by 2, we get 2 here. So finally, we get 6 over 35. So the probability is 6 over 35, okay? All right, let's come to problem 5. So we want to find the total number of n such that this number 2 to the nth power minus 1 is divisible by 7, but not divisible by 63. So notice that 63 is basically 7 times 9. And we know 7 and 9 have greatest common divisor, 1. They're relatively prime. So we have, okay, 7 is the divisor of 2 to n minus 1, and 63 is not a divisor of 2 to n minus 1. This is equivalent to the following. 7 is a divisor of 2 to n minus 1, and 9 is not a divisor of 2 to n minus 1. Okay, this is equivalent. All right, let's consider this statement. Okay, notice that 2 to the 3 or 2 cubed equals 8. This equals 1. The remainder is 1 when it's divided by 7. Okay. So we see that if n equals 3k, 2 to the nth power minus 1 is 2 to the 3k minus 1, which is 8k minus 1. This is equivalent to 1k minus 1. This is 0. Mod 7. So if n is a multiple of 3, 2 to nth power minus 1 is a multiple of 7. Now let's consider if n is 3k plus 1. We see that this equals to 2 to 3k plus 1, so it's times 2 minus 1. This corresponds to 2 minus 1, which is 1, mod 7. And if n is 3k plus 2, 2n minus 1, this is 2 to 3k times 2 squared minus 1. This is 3 mod 7. So there's only one case to satisfy the numbers divisible by 7. That is, n must be a multiple of 3. Next, let's consider the divisibility by 9. So notice that n equals 3k. So 2 to the nth power minus 1 is 2 to 3k minus 1, which is 8k minus 1. We know 8, the remainder of 8 when it's divided by 9 is just 8 or minus 1. So here we prefer to use minus 1 when divided by 9. Okay, and we know this number is not divisible by 9. That means this remainder is not 0. And this happens only when k is odd number. So k has to be odd number. If k is even, the remainder is 0. It's divisible by 9. So here the requirement for n is n equals 3k and k is a odd number. Let's count how many such n are there. So let me do it here. N equals 3k and 3 times k. So let's take k equals 2t plus 1, right? This is formula for odd number. Shows this is 2t plus 1. And this number is positive, is larger or equal to 1, and less than 1,000. That helps us to find the t. So the smallest t is 0, okay? T cannot be negative. The smallest t is 0, and then t can be 1, 2, 3. The largest possible t to satisfy this number less equal, less than, this is strictly less than 1,000. The largest t is 166. Okay, 166, because from here we can solve the range for t, right? 2t plus 1 is less than 1,000 divided by 3. So t is less than 1,000 divided by 3 minus 1 divided by 2. Okay, so from here you can see the upper bound for t. Okay, this is like a 333 point something minus 1. So this is the largest possible t is 166. Okay, so totally we have 167 valid n. So the answer is 167. Okay, that's the answer. Now let's go to problem 6. We'll consider the following relation. This is always non-negative for all x. So we can consider the roots of the following equation. X minus 2 times x squared minus 2, ax minus 2. Let's consider the roots. So this means x minus 2 equals 0, or this quadratic function equals 0. Okay. From the first part, we see that x equals 2. From the second part, we see that there are two solutions. So it's 1/2 a plus a squared plus 8. Squared plus 8, right? And then we also have a minus square root a squared plus 8 divided by 2. Okay, and we see that this later part is negative. It's negative. Right? Now this function is always non-negative, and we have these two positive roots. This is positive, and this is also positive, right? Positive. So in order to have this always non-negative, these two roots must be the same. Okay. Otherwise, whenever this function touches the root, the sign changes. Okay. The only case that the sign doesn't change is these two roots are equal. For all x, this means 2 equals this root. Okay? Or 2 is a root to the quadratic equation. So we can plug in 2 and find the value of a. So 2 squared minus 2a minus 2 equals 0. This solves the value of a. A is equal to 1. Okay. All right, let's come to problem 7. For how many 4-digit number capital N such that this new number is divisible by d for every d between 2 and 11. So let me write down these relations first. So we have, okay, 2 is the divisor of n, 2, okay? And 3 is divisor of n, 3. And 4 is a divisor of n4. And 5 is divisor of n5. And the 6 is divisor of n6. Also 7, divisor of n7. 8 is a divisor of n8. And 9 is a divisor of n9. 10 is divisor of n10. Also 11 is divisor of n11. Okay, that's all requirement for n. So we want to find how many such n are there. Now let's consider each relation. So some relations are automatically true, so we don't need to require anything for n. For example, the first relation is automatically true for any n. This is true because a number is divisible by 2 as long as the last digit is even. Okay, and from the second relation, we see that the divisibility test for 3 is as follows. A number is divisible by 3 if the sum of its digits is divisible by 3. So since the last digit is 3, we need n also divisible by 3. Okay, that's the requirement, right? And for 4, divisibility test for 4, we require the last 2-digit number is divisible by 4. So that means the last digit of capital N should be even. So this requires n is divisible by 2. And for the divisibility test for 5, a number is divisible by 5 as long as the last digit is 5 or 0. So this is automatically true. We don't need to require anything. And for 6, okay, we already have, this is equivalent to, from the previous 2, because capital N is divisible by 2 and the capital N is divisible by 3. That means capital N is divisible by 6. So here, actually, we don't need to require anything. This already gives us 6 divisible already, and it's already divisible by 6. So this implies this is true. Okay, we don't need any additional requirement. Now let's come to 7. For 7, this is equivalent to 7 is divisor of 10n plus 7. Okay, and basically we can remove this 7. Doesn't change anything because 7 and n are relatively prime. This is equivalent to n is divisible by 7. That's the requirement. Okay, now let's go to 8. A number, is divisible by 8 as long as the last 3 digits, the number is divisible by 8. So here we see that we need n to be divisible by 4 in order to have this divisible by 8. Okay? This means 4 is the divisor of capital N. Okay. So okay, maybe let me write more. This means 10n plus 8 has divisor 8, right? And that means 8 is a divisor of 10n. Okay, because in 10 we already have a factor 2 here, so this requires n divisible by 4. So 10n is 5 times 2n, so it's divisible by 8. So we require n is divisible by 4. Now let's go to 9. A number is divisible by 9 as long as this, okay, it's equivalent to the sum of its digits is divisible by 9. That's exactly the same as 3. So we have this 10n plus 9, this is divisible by 9. So that means n is divisible by 9. Okay. And okay, this is automatically true because the last digit is 0. It's automatically a multiple of 10, so it's automatically true. For the last one, we have 11 is a divisor for 10n plus 11. This implies 11 is divisor of 10n. 10 and 11 are relatively prime, so this implies 11 is a divisor of n. So we have this many requirements, and let's combine all of them. We see that we have requirement n is divisible by 11, n is divisible by 9, and n is divisible by 4. So once you have n divisible by 4, we automatically have n divisible by 2. So we don't need to consider n divisible by 2. So, and also n divisible by 9, so automatically it's divisible by 3. So this is automatically satisfied. And we also need to require n divisible by 7. So basically we only have 4 requirements for n. So and we see that 7, 4, 9, and 11, they are relatively prime. So that means, okay, let's consider the least common divisor. Okay, no, least common multiple. Yeah, least common multiple of these numbers, 4, 7, 9, 11. This equals 2, 7, 7, 2. So we see that n is divisible by 2772. That's the requirement for n. And see, we can find the total number of such n. So n could be, okay, n belongs to numbers like 2772 or 2772 times 2. That's 5, 5, 4, 4, or 2772 times 3, 8, 3, 1, 6. And if 2772 is times by 5 or times by 4, that's too big. That's not 4-digit number anymore. So that's okay. I mean, yeah, it cannot be multiplied by 4. That's too big. So we have totally 3 such numbers. The answer is 3.